for some of you afternoon. I'm in Switzerland, where I'm enjoying a sabbatical, which is a wonderful time for a professor to spend a year outside of the turmoil of being a professor in your university and learn and resource, I would say. That's what I'm doing here. So it's my last 2 weeks now. I'm flying back on the 30th of November back to Quebec City. What I've done is I chose a topic that is, I think, actual, digitalization. It may not be directly applicable to all WASH applications, but I think it's still something that all students working in there, or people that are involved in the water sector, should be aware of. And it has impacts in our world, in our lives, and also in the water sector. So I wanted to explain a bit those things. And I wanted to also talk about the fancy theory. That is, I will not go into the theory. This is not the idea of the topic. It's more like the concept of digitalization, etc., that I want to bring to you. Some of the issues that are around it, and then show you some of the work that we do in our group on machine learning, AI topics, which I think are, well, trying to get these things in practice. Personally, when I finished my master thesis, I got exposed to artificial intelligence. This is a long time ago. It's more than 40 years ago. No, 35 years ago. It didn't work at all. It was just a failure complete. The methods were not ready. The data were not ready. 15 years later, I tried it again with one of my first PhD students. And we tried really hard, 6 months, and we just had to give up. And now, the last 3-4 years, I'm applying these methods, and it works. So the interesting thing is, I think something has happened in our field that made that the data are good enough, the methods are good enough that we can really apply it and get used. And I will illustrate some of the results that we've got. I think that's the storyline. If there's things that I'm not clear or that you need explanation to get on, just put a message in the chat box. Kaitana, I will not check the chat box, that's too confusing, but Kaitana will look into it and will call me if something is not clear and interrupt me. That's perfectly fine. And then we'll have some time. I think for 40 minutes presentation, and we have 20 more minutes and whatever. I have plenty of time if you want to discuss longer. Enthusiasm is to be shared if we have it. So I'll put my presentation on. Can somebody confirm it's working? I don't hear anything. Okay, it's working. Good. Okay. So there's lots of fancy theory. If you're in Google, etc., you're working there, you're doing lots of fancy stuff. I will not talk about it, as I said, but I just wanted to make sure that there's this discrepancy between all the theory which is around and then the problems that you have when you apply to this. By the way, this is a picture of Quebec City and our university. And you see now a lot of names underneath. These are all the people that are now in my team working on some aspect of AI, some aspect of digitalization, digital twins. Okay, let's go. Let's get this going. Click. You said you were going to record this. Is it recording? Yes, it's recording. Good. Terminology. I'm a person that likes to make clear what I mean with things. And this one, maybe it's my problem of being a teacher. And so I want to talk about terminology. And digital transformation of the water sector requires a number of words. And you get things like digital water, smart water, Internet of Water, Water 4.0, and all these terms appear and are being discussed. And at some point you start thinking, why is this terminology so much creating? Well, it's a hype. There's a big hype of digitalization of the water sector. A lot of companies get onto it. The mayors and the CEOs of water utilities talk about this. And have we not seen this before? I said, I was doing this in 1988. And that didn't work. So are we not getting the same problem that now people are on the hype and are not seeing this? Okay, where am I? Here we go. So let's talk about words that deal with digitalization, digital transformation. Let's talk about digits first. Well, digits is this, right? And we have 10 of them. And if you look into programming, you start counting at 0, which is already confusing for people. So digitization could be something about using your digits, which is this field in our smartphones is close to AI. When you talk about digits, it's also about binary code. And I don't know whether any of you know this figure, but what is important is the number. It's his favorite number. And my previous favorite number was 37, but I changed my mind now I'm fully in favor of 73 because it has many goodies. One of them being that if you write it in binary code, it becomes a palindrome. It's 1001001, as he says. If you turn it around, it's 1001001. And if you want to have this 1.1 minute great time of Big Bang, just click on it, you'll get the slides. You can just click on it. It's a really good piece of humor that they put together. So digitization is about translating continuous signals like noise or sound into numbers. The recording that is now happening is basically transforming a microphone that reacts, and that is put into numbers, and it's putting into binary numbers. So it's all ones and zeros coming out in a certain sequence, of course. When you talk about digitalization and digital transformation, which are the terms that are being used in our field as well, this is about the use of digital technology to change a business model and provide new revenue and value producing opportunities. This is what we call digital business. It's about transforming our business into based on digital technologies. That's what digitalization is about. So that's the term you should use. I think it's important to realize why so many people are interested and why industry is interested in digital transformation. And Wesley from Trojan Technologies in London, he was at the Young Water Professional Conference, International Young Water Professional Conference held in Toronto in 2019. By the way, in 2023, there will be another one. So it's coming up, and it will be in Vancouver, I think. Yes, close to where most of you are. And he gave a list of the whys. So first is an economics reason. Internet of Things connectivity and functionality are very cheap compared to what was available before to get data and work with data. The building blocks are existing. You can just get them off the shelf. The sensors are everywhere. You can just find them and install them. We want systems to become more robust, and we want them to be digital. Because when we are able to connect to those systems, our fridge, our car, we can change it. We can change the properties. We can update a program inside. It can be done in real time. So something happens, you can change the program if something doesn't work anymore. And that means that those systems become flexible and can be adjusted for unforeseen circumstances. We can change things because they're connected, and they become therefore more robust. In the field of water, it's even important to state that the decentralization of treatment, which we are sometimes focusing on, we have these big centralized systems, but there's also a need for decentralized systems. Well, if they are digitally connected, those systems, we can make it practical to have them decentralized, because we can put expertise and monitoring systems in place that are looking from a distance and make those systems also reliable and robust. There's an issue with workforce. I'm getting close to my retirement age, so in many places we see that the wave of people that moved into the water industry, they start retiring, and so all those expert operators are moving away, and so the art of keeping systems running needs to come from those experts. And if they're gone, we want to replace them somehow, because we may not have the people to replace them. So we'll try to be efficient, and we can do that by having experts focus on many more systems than the one typically followed by each expert operator. So we'll have expert systems, we'll do remote access, we'll have telepresence, and only go in when we need to. And there's also a new business model emerging, where we have a product that's just basically sold as a service. You basically have companies that will install a sensor, a machine, and they will not give it away. They will keep it as their property, but they will give the service of the data coming out, the functions coming out. So you manage a product as a service, and this requires efficient and comprehensive digital connectivity. So these are the whys of digitalization. We talk in big numbers. So this is a thing I picked up in 2015 on the expected savings in 2016. We talk about billions, hundreds of billions of dollars in the drinking water sector and the wastewater sector. So they're about the same in size, these two sectors, in fact. And where are these savings generated? Well, if you look at it, it's working with the previous success of digitalization, because we had already a model-based design of facilities. We have process control that is using data from sensors. And that's not new, because this little book that is high on my list of books I would like to share with people, I have a PDF of it. It's about a book that was presented after a workshop in 1973. And if you read that, there's so many things that are still perfectly aligned with our current developments. But we're having new systems that can benefit from digitalization. If you look at utility management, like the whole water system in a city or a municipality, and we have a utility that runs this, these are systems that are quite more complex and much more complex to manage. And their big data and data analytics, they are very useful. They allow for much better long-term planning because you can look back at history, learn from it, and then see where things are evolving. You can engage with customers because you know what they're doing and what they want. You can give them a dedicated bill, so focused bill invoice. You can optimize your infrastructure much better because you have the big picture of everything. You can see where optimizations could be done. And for instance, you can just do proactive maintenance. We're involved in a project where we try to follow the behavior of pumps and valves and see where they start having trouble, where they're moving slower, where they're like getting stuck and then move on. So these things allow you to send people out to repair them only when it's needed and not having to go around and around and around just to check whether things are still okay. You become much more efficient. A nice thing I read in a Deloitte text, to make the right decisions, the right people need to have access to the right information at the right time. This is where at utility management level, those data analytics allow you to present that in time and the right data, not dashboards and stuff we do typically for them. When I was in Switzerland 4 years ago, I was there for 3 months and we did a horizon scan. A horizon scan is where you try to find out which challenges exist in the research area. And you do that by literature review, by discussing, by opening up and doing workshops. And we wrote a paper that I think is still worth reading. And it talks about, among others, digital transformation in the urban wastewater management. It's about emerging opportunities and threats. So these things is what we discussed. And what came out was that we wanted to not make a list of all possible research topics. We basically wanted to make it a top 10. And the topics that were selected must be identified by many people as important. And we should not know much about it. So there's still a lot of uncertainty and it's not clear what really the issue is. And people are not familiar with the problem. So then it became a topic of an emerging topic that requires further research, which is of course what a university professor always wants to have. Now, what was interesting in that study was that half of the topics of those 10 were related to data and digitalization. And what if you split them up, you could see that half of them were about pushing data, so new data sources that are becoming available because there's a lot of development of new sensors and new ways of interpreting results, but also other requirements or demands for research were, I need more data. I want to do this. I think there's an opportunity for this, and I don't need a data, so a data pool topic. So that you can read more about it if you want in that paper. There's a lot of challenges as well with digitalization. And one of them is maybe going to be moved away when people retire. But if you look at current workforce in the field of water, there's digital anxiety. People are afraid of having it all coming in. Lots of things to learn. It's not everything is safe yet. What is it called? Cyber attacks are happening. So these are the things that people are sometimes afraid of. There's still a lot of work to be done on standardization. We may think that everything is standard, well, it's not. When we start communicating and storing data, it's pretty messy. So there's a lot of things to be done still in that area. And there's a lot of problems with data quality. You can generate lots of data, but if your sensors are not maintained well, you will have bad data. And you know what happens to a discussion or decision making? If you have garbage in, well, your decision will be garbage as well. This is a nice graph from Chris Villet, who is the chair of a task group on metadata and data quality. He made this nice thing about what our AI methods do. They basically transform information into useful things. And of course, you need to organize the data because it comes from many different sources, big data stuff. But the important thing is that in between, you must filter, you must get rid of. And I'll give you an example later on of what you can do with this. So the data quality assessment should not be forgotten when you talk about digitalization. There's a protection of public safety. If data about drinking water use, if you have personalized information coming from your use of water at home, well, it says something about whether you're at home, first of all. What you do at home, you can read about, you can learn about the way that water is consumed. So this is about public safety, right? What happens if you have an attack on a water production facility? And we have examples now of cyber attacks where the whole wastewater treatment infrastructure was jeopardized because they were able to get rid of all the Microsoft software. And I have an example of people I work with, they were attacked and all software that was coming from Microsoft was blocked. Luckily, all the systems that were doing the water and wastewater treatment kept running because they were running on another system. And you should think about, if water is really affected, you really affect society. Yeah? Another thing that is interesting, I think, to think about is that if you look at the pace of development in data analytics compared to what we do in knowledge acquisition in our research, data analytics development is so much faster. And the reason probably is because if you develop a method in one electrical engineering discipline, or in software engineering discipline, and you do it in pharmaceutical industry, and you can just copy those methods often. What we do is use those methods that are coming from different application areas. That doesn't work for knowledge acquisition. You must know the domain before you can build upon, and it's building up further and further. So every PhD student going through the learning phase of coming from the studies you've done at university into this postgraduate studies, it's a long distance before you're up to speed with the latest development that you can add upon your own thing. So there's a big gap in development pace. And so one of the questions we have to ask ourselves is, we might be interested in those mechanistic models that are based on first principles and the knowledge we have. But if it's so easy to collect data and create models that help us decide on things using data analytics, will there still be place for mechanistic models? And will we still acquire knowledge if it's not needed anymore because we think we can do everything with data analytics? Exponential growth, you can imagine that, and it's reported that this is going faster and faster. So if you just look at publications, just tremendous pace at which these developments are happening. In the water sector is a bit different than other sectors. People that are in the field for a while, they realize that changes to water systems are frustratingly slow. So you cannot change the industry very quickly. The reason is, of course, that the equipment that is there, the installation, the infrastructure we've built, it has been built to last 20, 50, 100 years. You don't remove a sewer system. It's built to last long. You don't remove a treatment facility because the investment you've done is for 30, 50 years. So it's intrinsically conservative. So if you look at water system change, it's 10, 20 years before you get a new technology and a new thing in. It's generational work. If you look at digital transformation, that's much faster. It's 1 year. Every year there's a new iPhone coming out, right? So every time things are changing so much more fast than what you have in the wastewater systems. But maybe that's a good idea. Maybe it's good that if you look at security stuff, you must be careful with water systems. And there's ethical issues as well that you first have to think carefully before you bring them into the field. So it may be frustrating on one hand, on the other hand, it might be a good thing that we are not too quick. But we see an important paradigm shift anyway. So we see that before the digitalization hype started, it was not really easy to get instrumentation, control, automation, that's ICA, modeling into the practice of utilities. Many ideas never made it. And they're still stuck in the papers and the books and the PhDs and the papers. So these bottom-up things of new ideas were just blocked because things were slow. With this digitalization hype now, these technologies that are using data are really hot. Utility management people have a buy-in for these. So the CEOs and utility boards, even the mayors, talk about digitalization and digital twins. They want to lead the way. They want to show that they're up to speed. It's a top-down thing happening. You see that people are investing or recruiting chief digital officers, so that this can happen quickly. And what is also happening is that since it's a top-down thing, people that are coming up with new ideas, they're allowed to develop them. Even if you have any doubt, you can still use it. You see these things happening. So before I go to some applications, my conclusion of what's happening now is that I've gone through many years of frustration. You can understand. I was a modeler. I was trying to use instrumentation, control, automation many of the things I did that didn't make it. They were just not accepted by the conservative nature of utility managers and people that were responsible for water management. What we see with the digital hype now is that since a few years, I can get things done quite easily. Students come in and want to do something with AI techniques, they get opportunities. Companies that have a digital or a data-based approach, they get nice projects to work with. So it's an opportunity. You just have to be careful not to ruin it, as I've lived as well in the 80s and around 2000, where you try things that doesn't work and you basically have really bad results. We should be careful not to have them. So we can make digital water happen, but we have to take advantage of the fact, but do it carefully. And some people that know me, they know that I'm a Formula One fan. And if you know Lewis Hamilton, that's his car when he was successful 2 years ago. Often when you heard him talk, it was his race director said, it's hammer time. It's like, give it everything you got. Now is the time to reap the benefits of the things you've learned and worked with. So that is, I think, is something that we should try to deal with. So this was the introduction. I would like to talk about real life application, I think, because it's important to realize what can be done. And I'll give it a few of the diverse things that we are trying in our group, and the different people underneath there have contributed to those. First, I want to show you a graph that Jean-David Terrien made in a paper in 2020 in Water Science Technology that gives a data pipeline. It shows you the way that data from different sources, from the lab, from online data, from weather information, from meteorological forecasts, from data analysis that people are doing. You collect those data, you process them, you store them for later usage. It becomes information. You do data mining, you make models eventually. You start understanding how your process works, that's giving knowledge, and then you can do something intelligent with it. These are actions that come out. These are process control, optimization, etc. So I'll use this graph for a few of the things that we've been working on to illustrate different aspects of where data are being used and how you can bring them to intelligent activities. So first, data quality control. I already said that data garbage in is garbage out, so wastewater is nasty. This is a freshly bought sensor for nitrogen, for ammonia, and this is after a week in the water. This sensor doesn't work anymore. It doesn't give you good results. The probes that are in there, it's pH probe and ammonia sensitive probe. There's some other things in there. They're clogged with biofilm, etc. It leads to noise, outliers, faults, and gaps in the data. You have different problems. You might have a bias, you might drift, you might have a complete failure. The sensor just gives a fixed value, or it becomes very noisy. These are all problems that you can work with. And sensors fail by definition if you work in the wastewater area, or need maintenance during operation, and lots of maintenance. Like some place where we've measured, we could get a sensor going for 3 days. We had to go every 2 days. We had to go in, even though the manufacturer said it's going to last for a month. No, it didn't. Collected data need validation, and if you want to use them in automation, like to decide immediately what's going to happen, you need validation in real time. So you must know whether data can be trusted or not. So that's what we do with data validation. And if you have high frequency sensor that gives values every 10 seconds or something, it's quite a lot of volume of data you have to work with. If you get a data value every day, you can do it maybe manually, look at it in the morning. But if you have data coming in every 10 seconds, you can't have a person doing that. It's just too much work. So you must automate this. So what we did was we developed, as other people, we developed methods to basically clean data and smoothen the data and basically try to find out fault if they exist by extracting information from the signals. This was Yanelsi Alterez that worked on this, and it was quite some steps, and we had a method that worked, but it needed quite some work for every sensor that we wanted to apply this to. We had to have Yanelsi working on it to make sure the method was working properly. So we wanted to get rid of all this manual work to make that the model was tuned for the data sets we got. So what we got out of this, if it worked fine, you got the green line. All these crosses are basically bad data. They are eliminated. You get a smoothed curve, and then you can use it. And you get some idea of faults that are coming out. And you see that some periods of time it's not working fine. So this example just is about 8% of the data are out. That's a lot, 8%. But you would be really happy with it because 8% is quite low compared to what you typically find in wastewater data, where sometimes half of the data has to be thrown away because it's not trustworthy. So what we wanted to do is to make sure that we didn't need the NLC doing the work every time. So you wanted to have an automatic method. And machine learning can learn from the data itself to see whether other data are good. So what you do is you basically train the method using these data analytics tools. You train the method to say, this is a good value, that's not a good value, and smoothen it. So what you basically give it is a data set that, according to the expert, that's the only thing he has to do, is to say this training data set is good, and then it will learn the method, and the method will be able to then treat all the data it collects. So there's much less need for an expert that is costly to make these methods work and apply them in practice. However, if you make that work, you get data gaps. You might have data gaps because the sensor doesn't work, but it might also be because your method says that these data cannot be trusted. So you get all these holes in your time series, and that's not easy because you want to work with continuous time series. So one of the things that models and machine learning methods can do is to fill data. You basically add information that you can base on just interpolating, having a correlation with another signal. You can just do very simply saying, I'm going to keep the last value I got, or you can use machine learning to learn about what typical behavior you have, and you have these curves that basically are now becoming complete that you can use for whatever use you have for these complete data sets now. So that's what we discuss here, but these are the things where we did some work on data treatment and gap filling in this block. The other thing we did was to work, and I'll give you an example, is in many applications you need to know how much water you will get at any moment in time, how polluted it will be. So it's what we call an influence generator. It's a model basically that tells you for the next days or next hours or next year, this is how the wastewater would look like. Given that there's rain and there's snow and there's melt and there's activities in the cities, there's households that go on holidays, there's industry cleaning up, all this can be used to create a model that allows you to generate a time series of flow and concentration of pollution that is realistic. And that helps you to then design a treatment plant, a proper treatment plant. It helps you to look at, imagine climate change is having a big impact on the rain events. How would that treatment plant work in 30 years when the conditions of the amount of water coming down the drain are different? That's an influence generator. So the rain influent wastewater is the main disturbance of a treatment plant. It's about flow rates, it's about pollutant concentrations. And you cannot collect data easily. There's a lot of work, and you might do a few days of data, but then you're basically running through the budget and the time effort you can spend on this. So to get high frequency long time series, which we need for our design work and for our scenario analysis, we should generate long time series. And we must take care of diurnal variability, weekly variability, seasonal variability. And so what you try to do with these methods that I'm going to explain you is that you're going to generate long time series based on limited data. And that's what we call an influence generator. I will not go into the details, but the key part is that, again, there's an artificial neural network here. This is a PhD study recently finished. And the only input it needs, once it's trained, it needs weather data. So it needs the temperature and it needs the rainfall intensity over the last days. And it will be able to generate as output the flow rate and concentration of pollution. That's what it does. Of course, you've learned a yearly seasonal daily pattern from the data you get, because you see typically the daily flows and the concentration going up and down. You might have some idea of the flows that are changing during the year because there's groundwater infiltration. All these things can be captured in these models, and that makes that the influence generated leads to realistic values. I'll show you one of the examples of case studies we did. This is Quebec. It's an old picture. This is when the treatment plant was just built in 1995. But just to show that for this treatment plant, we were able to generate the influence for the future. So what you see here is 1.5 years of data from January 1 year till end of the year, and then 6 months more. And you may recognize this is the flow. The blue things coming down is rainfall. The flow goes up, of course, when it rains. And you see the flow increase in April. That could be due to snow melt. And this is a very wet period that happened in October of that year. So we have a lot of big storm events, and it kept raining, so the flow went up. And here we have again the next year's snow melt. If you look at the concentrations, and you see in black here the real measurements of concentration of pollution coming in. The red is the model, the influence generator. This is validation data. So this is the model tries to find out without having seen these data, and it gets pretty close. You see, of course, the dilution because of the snow melt happening here, the dilution because of this very wet period. All this comes out well. And the flow is pretty good. So the flow, just using rainfall data, you get this flow right, and you get the dilution right as well. This is for the concentration of TSS, I think. If you look at ammonia, similar thing. We have this is another period of the year, and it's also for Quebec. You see again dilution here in April, March, April. But I want to focus now on the part of gap filling. So these are the data that the people at the treatment plant they collect. So they work in the week, Monday, Tuesday, Wednesday, Thursday, Friday. There's a gap in the weekend. And then of course it rains in the weekend. And what would be the concentration that you would need for that day? Well, thanks to the models, we can basically predict what's going to happen. So we can predict the missing data because we didn't have people in the weekend to go do the work. Okay, let's look at the use of models and of making intelligent decisions. It's the last part of what I'm going to talk about. I have two examples. One is about disinfection. And what we're going to talk about is we use models for prediction. So we use control, which is acting on the process to make it work better. And we're going to use models to predict the behavior of that plant and therefore to make the right decisions on how to change addition of a chemical, maybe change pump flow rates, etc. This is disinfection control for a treatment plant in America, HRSD. Disinfection is in many places needed, and it requires quite some chemicals. You do hypochlorite addition, and what these people wanted is to predict gallons per hour. We're in America, it's gallons per hour. So it's the hypochlorite dosage and flow, and they tried to make a model that would use this information. So it was learning from the past. You gave it all this information, and it would give you a model that would describe how much hypochlorite you would add. I'll just give you two examples of data sets of what they did. So this is the real dosage that they used to train the model with. This is what the model was able to describe for those days. So it was pretty close. So happy with the training quality. And then what you saw is that the observed residual chlorine in the water is this, which is important because what the target is this number. It's 0.75, 0.75, yes. So they're around the number, so it's good dosage. And if you would use the model now to optimize the dosage, you would be able to do a bit differently. Would add a bit more in the beginning and a bit less at the end, because you see that in the beginning we're below the desired value, and at the end we're a bit above. So you could see some benefits. It's quite different than another situation where we were at that plant, they were overdosing completely. Like this period is a period where there's complete overdosing of hypochlorite. So you waste chemical, you make the water not taste well, and you get, by using the model, you can do a much better job. You would, to reach this black line, in theory, you would be able to use this dosage, which would save you a lot of money and would keep you on track. Of course, the controller will not perfectly work, but with those predictions of what you should do, you should be able to get much better than in the situation that you see here. So this is getting into practice. So this is the final test they did, and then they're putting into practice at the Nonsmond plant in West Virginia. I want to go with you into wastewater treatment itself and dosage of aeration, so air supply, and methanol dosage. So methanol is used for removing of nitrate in wastewater to get rid of the nitrogen load to the receiving water. And aeration is very important because half of the operating costs of a treatment plant are typically aeration. So it's everything you can do to reduce aeration is a good thing. This is a mechanistic model, first principles, based on mass balances and reactors and series and everything you learned at environmental engineering classes. However, this would not be a very good tool to put into a digital twin, like a model that describes real behavior, because these models are built once and they're then being used for design, but they're not meant to be updated on a daily basis, let's say, to make sure that they are closely matching reality, which is what you need if you want to use them for operator support or decision-making, automatic decision-making. So this online updating, like all the time, making sure it works and is close to reality, they're just not, it's just too heavy for these models. However, there's methods that have been developed to use the first principles model because that's based on mechanisms, so it has a good extrapolation power. But you would then use a neural network to correct for things going wrong. And with inputs, you would be able to calculate outputs, and these outputs are predictions of how it's going to behave. So how much, if I give this amount of methanol, what nitrate will come out? If I give this amount of air supply, how much will be my nitrification will go? So this is a serial configuration. This is the one I prefer on the right. It's the parallel configuration where we have the mechanistic model that just runs, and the neural network will correct. It will just add something to the predictions and make sure they're closer to reality. And that's what we've been developing. So these techniques, you see again, around 2000, there was a lot of activity in this field. We applied this to one of the biggest plants in the world. It's Saint-Naval. So this is Paris. They have 6 treatment plants, and this big one here is 1.7 million cubic meter per day. That's 5 million people that are being treated. This is the plant. You cannot really grasp it how big it is, but you just look at the cars next to it. It's pretty big. And it's really low footprint because they used biofilm systems that are very compact. So it's pretty impressive as a system. So what we have is the real system, and what we make is a digital twin of it. So the digital twin is basically a copy that runs on a computer of what this physical system is doing. And what we've done is we made a hybrid model. A hybrid model is this combination of a mechanistic model that we use in these typical wastewater simulators, and then a machine learning model that we did in MATLAB, but you could do it, we now start working on Python as well. And basically what you want is you want to use the mechanisms in here to have a good extrapolation power, but you want to use the ease of learning errors that this model makes and basically have corrections done with the machine learning model. So what we provide these models to work with is we need to provide information of what's coming in terms of temperature, flow rates, different concentrations. We get this from the data that we collect from the wastewater system. We feed this both to the mechanistic model and the machine learning model. And then we've trained this machine learning model based on comparing the data coming out of the mechanistic model with data that we collected from the treated wastewater. So we look at effluent measurements of COD, of TSS, of nitrate, etc. And the delta is fed to this machine learning tool, and it will learn the errors. And based on the conditions that might happen in everything that we know about this, we will be able to say, okay, now the error is this big, 1 milligram of nitrate too high, 0.5 milligram of nitrite too low, etc. Once the training is done, we can now use the model to basically correct what's coming out of the mechanistic model, and we basically get a correction of this that we apply. So the nitrate will now be closer, and you will see that we use this to predict effluent quality. Just an example, this is on black is the data collected at the treatment facility in nitrate in the effluent. Blue is the best mechanistic model we get, so it gave the blue lines. Not very good, the major dynamics are there, but you would say, well, this is not very strong. This is what you get when you do this hybrid model. So you're really on top of it, which is normal because we're talking about calibration. So basically, this model has learned a lot and knows how to do it. The proof of the cake is in the eating. This is the validation. So this is, with this blue model here that is not working fine, well, we tried on different data, it still doesn't work very fine. It still does cover something, like this goes down here, it goes up there, but some things are completely missed. In the hybrid model, it's not as good as it was in the calibration, but you still see that it's much better than the mechanistic model that we might have been using, but the hybrid model is doing a much better job. So we have now a tool for this big plant in Paris that allows us to predict what the nitrate will be in the effluent, given, for instance, methanol dosing rate. Now, what it means is that we can use this model now to optimize that methanol dosing and reduce the amount of methanol we're going to buy in, going to consume, get a better nitrate removal, etc. All benefits you can get, and much better than what we did before. So what we're working on now is basically working on 2 control systems. One is doing the aeration control, and the other one is doing the methanol dosing control. They're not ready. We have half a year to work on this to make it all work, to find out how we can use the information that's coming out of these hybrid models to include them in this improved aeration controls. And we have good expectation that we can reduce both energy consumption and chemical dosing. Okay, to finish with, things are moving quickly. It's finally happening. I was hoping for this to happen, and I was very reluctant 5 years ago when I saw the first things happening that, am I going into this? Okay, I went in and it was a success story, I would say, because we are applying it to different applications. It seems to work nearly everything we touch. I think we do a good selection of things we touch with this, but it seems to work quite fine. The challenges are not small. It's quite difficult to work with these things, and there's a lot of challenges in terms of getting it accepted still, even though there's much more interest. Data collection remains difficult. There's still problems with the sensors are not optimal. There's good developments, but it's not optimal yet. But the AI and machine learning tools have become really mature, I would say, and they can be used in many practical situations, and this to great benefit, I would say. We have to be trained in this. I think our students must be exposed to Python coding. They must be exposed to what digitalization can be. They have to be exposed to the dangers of cybersecurity. I think that's key to make sure that we get good use of these tools. And it may be good if you try to do things is to under-promise and over-deliver, rather than saying this is going to solve the problems of the world, and then if the mayors and the CEOs see it doesn't work, they might completely kill the opportunity that we have now to do some quite innovative things and change the water systems with this hype of digital transformation. This is what I had to tell you. I hope there's some questions. I'll stop sharing and look you in the eyes.
Fantastic. Thanks, Peter. We'll open the floor for questions.
I can open the slides again if you want to have a particular slide, but it's good to see the people that I've been talking to because I didn't see you before.
Yeah, so if anyone wants to raise their hand or just unmute, feel free to jump in.
I have a question.
Go ahead, Anita.
Hi, thanks for your presentation. I've been thinking about what you've been presenting a lot, and I'm just sort of like the movement